right, so you've just seen how we can increase the size of the difference between the means in an experiment. And of course, this is good because if we increase the difference between the means, we're going to increase the probability of making correct decisions and decrease the probability of making an error, right? And all this means that as the group means become more and more different, our effect size is increasing, the absolute effect size. But remember, we also can, to a certain extent, manipulate the relative effect size. So the relative effect size takes the difference between the means and it divides by the standard deviation of the scores of your dependent variable. So if we could find a way to make scores on the dependent variable vary less, then we can increase relative effect size. So how do we do that? Well, one of the first things you can do is conduct a clean experiment. So what this refers to is collecting data and measuring, recording data in a way that is error-free. You want to be awake, alert. You want to be anal, right? You want to be very, very meticulous when you're collecting this data. So that leads me to a bit of a fun story. When I was an undergraduate, I was testing pain responses in rats. And I did it by injecting a chemical into one of their paws. And the chemical is an irritant. So it feels kind of like a bee sting where it hurts a lot for a minute or two, but then it fades away over the next hour. And so what I would do is I would test one rat at a time. I would inject them with this chemical into their paw. And for the next hour, I would have to keep track of how much time the animal spent with his paw completely raised off the ground, the paw just barely touching the ground, and then the paw completely on the ground. So as you can see, exciting research. And I discovered that after the first few rats, I was getting kind of tired. Actually, I was getting really tired and I didn't know what to do to keep myself awake because I'm, in the basement of my lab and nobody else around. Anyways, I decided that I was going to write down some notes. I thought that would keep me awake and alert. So I wrote something down as I was observing the rat, and then I realized that I have no clue what I just wrote. So keep in mind that this observation, to make observations like this, requires years and years of experience. What did I write? Rat is wearing no underwear. Yep. So what did I have to do with that rat? Well, by the way, that was an entirely accurate observation, but it also indicated to me that I needed to throw away that rat's data because it was obviously going to be riddled with error, and that would have increased the variability in the scores. And as the variability in the scores go up, what happens to relative effect size? It goes down, all right? So that is my sleepy rat story. Okay, the second thing though that you can do is test homogeneous samples. And what we mean by this is restricting the ways in which participants could differ from each other. And we're talking about ways that are irrelevant to the independent variable. So let me give you an example. Let's say that we want to test the effect of coffee on longevity, all right? So our coffee drinkers, do they live on average longer than people who don't drink coffee? And so to do this, we're going to have to identify a population. And let's say that population is made up of people all by the name of Ronnie. In fact, they are Ronnie clones. So somebody cloned Ronnie a million times. Now, if we test these different Ronnies, so we sample from the population, divide them up into two groups, one gets coffee for the next, 40, 50 years, and the other group does not. right? Not exactly the most ethical experiment, but anyways, if we were to do that type of experiment, well, if you look at the coffee drinkers, all those Ronnies are probably going to score very, very similarly. They're going to live to about the same age because they're just clones of each other. Now, the other group of Ronnies, they also will probably score very similar to each other, right? Because they're all clones. Now, they probably won't live as long if the hypothesis is correct. So if drinking coffee increases longevity, then we'll see a difference between the two groups. Coffee drinkers will live longer. However, within each group, the scores probably won't vary too much. And again, it's because all the participants are clones of each other. Now, contrast that with the same experiment, only this time I'm drawing my samples from the population of Montreal, Quebec. Now, most of you probably don't know what that population looks like, but Montreal is a very, very diverse city. Lots and lots of different cultures. The people in Montreal come from different ethnic backgrounds, racial groups. They speak different languages. They have different religions, different attitudes, norms, expectations, you name it. All the people, well, a lot of people in Montreal are very different from each other. So if I were to test them, then not only might I see a difference between the two groups, but within each group, within the coffee drinkers and the non-coffee drinkers, scores are probably going to vary quite a bit. And it's because these individuals are very different from one another, all right? They're what we would call heterogeneous, all right? So homogeneous means same, heterogeneous means different. So if all of our participants are very different from each other, and again, within, let's say, the coffee drinkers, we can expect scores to vary a lot, right? And then same thing, if we look within the non-coffee drinkers, if the participants are very different from each other, those scores will vary a lot as well. So with all that increase in variability, we're going to see a drop in the relative effect size, okay?